more right-hand rule. So remember, when dealing with magnetism, we can't do it in one dimension. We can't do it in two. It's automatically in three dimensions, which we've played around with a bit of three dimensions with other types of motion, but we pretty much limit it to if you can do one dimension, if you can do two, we're just assuming you can do three. But that's not the case with magnetism. We need to start in three dimensions because it doesn't even apply in one and two anymore, right? And so often enough, we talk about, instead of left and right and back and forth and up and down, we tend to talk about clockwise and counterclockwise motion. I'm not sure how the video would do it. Clockwise for me is this way, so clockwise for you would be this way. Either way, it's round and round in a circle, right? If we have a circuit, and maybe I should draw in some batteries and a resistor. Here you go. Here's a battery, and here is a resistor. There you go. There's my circuit, a battery, and a resistor, right? Our current goes around in a circle like this, right? It goes in a clockwise, counterclockwise motion, round and round and round like that, right? And so we have talking about up and down and left and right doesn't work anymore because it is this way here and this way here and this way here and this way. It's all kinds of different directions. But we can talk about counterclockwise or clockwise motion, right? It doesn't work to look at digital clocks. You got to look at those old-timey analog ones, right? And so our circuit, its current flows round and round. And as its current is flowing, right, each individual section of my circuit creates a magnetic field. And remember, when we're figuring out which direction our magnetic field points for a wire, we stick our thumb in the direction of the current flow, and we curl our fingers around, and that tells us the direction that our magnetic field coils around our wire. And so in this case, since it's flowing this way along the bottom, it's curling around, and in this middle section, which is the section we care about, our magnetic field is coming out of the page. Our current is flowing counterclockwise, and our magnetic field is perpendicular to that motion and is thus coming out of the page, right? Out of the page. Not this way or this way, but out. The other direction it could go would be in, and if it was flowing the other way, it would go into the page. Another way you can look at this, instead of looking at each individual section of my wire, you can look at the whole thing. Right? The whole thing has a current that's flowing around in this manner. Right? And so if I stick my thumb out and I curl my fingers in the direction the current is flowing, that tells me the magnetic field in the center of my loop points outward, which is the same direction we already knew, which is good that it's duplicating what's already known. Can't have the opposite answer, right? Which is good for Lenz's law, right? Lenz's law, I like to view as a type of resistance. It resists change, right? If there already is a magnetic field in this loop, right? There's already a magnetic field caused by an outside source, and that field is changing, right? Maybe there's already field coming out, right? There's already field coming from back here out through the page, just a constant field. If it's constant, nothing happens. It's fine, constant. But if it's changing, right, a current is induced to fight that change. So if there's a field coming out, right, and that field's getting smaller, right, less and less field is coming through my loop, and it doesn't like that change. So it fights it by making more field coming out to try to balance it. It won't catch up. It can't be enough to make it a constant thing, but it's a type of resistance. It resists this change. And so it's going to induce a current so that it creates a magnetic field coming out of the page because we're having less and less, right? If instead we were increasing the field coming out, then it wouldn't like that, it would fight it. And thus it would create a field going in order to combat that change, right? And we can use our right-hand rule again to determine which direction the current will flow. If it's going to create a field coming this way, like my field's going this way, it's getting smaller, so it's creating more, then I curl my fingers and it creates a current flowing this way, right? Counterclockwise. If it creates a field going in toward me, toward the page, perpendicular to the circuit, toward the page, then I curl my fingers around and it creates a current that goes this way, right? Lenz's law, it fights the change. Doesn't matter what it is. We don't care how big, what the magnitude of the magnetic field is. That's not important. What's important is how much it's changing, right? And then we can use this understanding of this resistance, this fight against change, will create a current either clockwise or counterclockwise, and that current will then create a magnetic field either out of the page if it's going this way, or into the page if it's curling around this way, right? Hopefully that's helpful.